Hi, it's Em. We're going to look at distance time graphs. This is page 11 of the Ratio to H pack. Okay, so distance time graphs, as they sound, are graphs of distance covered against time, and that time could be an hour of the day, or actual times you'd find on a clock, or it could just be a linear scale of time in seconds, hours, minutes, whatever. Okay, this one is showing times of the day. On some questions, it really pays to get an idea of what little squares represent. On this one, I don't think it's so important, but we can always come back to that if need be. And now, important parts of distant time graphs before we start. At this level, you will only really consider distance time graphs that are made of straight lines. Okay, what it means when you have a straight line on a distance time graph, one with a certain gradient, would mean that whatever it is you're talking about is covering distance over a certain time, but in a linear way. So it's moving at a constant speed. Okay, and when you get a horizontal part of the graph, that means that no distance is being covered. The distance from school or home or whatever is not changing, but time is still passing. So that means the object is staying still or is stationary. And then again, in this part of the graph, it's travelling again further away from school, and it's taking a certain amount of time. Now, the other thing you can see from distance time graphs is that when the graph is steeper, if we have a steeper part to the graph, that would mean that it's covering distance in a shorter amount of time to a less steep part where it might cover the same distance, so it might rise the same amount, but in a longer period of time. Okay, so any steeper parts of the graph indicate that whatever it is traveling faster. So steeper means faster. Okay, and the other thing you might find with distance time graphs is that they come back down. These graphs are not always just rising, they may come back down to zero or close to it, and that means that the object is getting closer to wherever it started again. Okay, so let's have a look at this first question. We've got a graph showing class 8A's journey to the zoo, and they stopped for a picnic on the way to the zoo. So you can assume that this is the point where they stopped for a picnic, because that's the only point on their journey where they're stopped. So let's see if we can answer these questions. What time did the bus leave school? Nice and easy to see that the starting time there is 9 AM. I'm going to give it in the same format that they've given it on the graph. What time did they stop for a picnic? So that would be at this stage here. So at 10 AM. How far had they travelled when they stopped for a picnic? They had travelled 50 miles. And how long did they stop for? They stopped for until this time, 10:30, so they stopped for half an hour or 30 minutes. And what time did they arrive at the zoo? So we can assume that this is the point where they arrive at the zoo, and that is 11:30. And how far is the zoo from school? So if this is the point they arrive at the zoo, then that is 90 miles from school. What was the speed during the first leg of the journey? Now this is by far the hardest question we've got on this. Now remember, you can either work out speed using what we know about speed as a compound unit. So speed is distance divided by time. And I think we'll go for that actually. So the distance covered there is 50 miles. So first leg of the journey is talking about the point until they stop. In other words, each change in gradient is a leg of the journey. And the time it took to cover those 50 miles was 1 hour. So 50 divided by 1 is 50 miles per hour. The other way you can work out speeds from a distance time graph is to work out the gradient of the line, and you can see that that is doing exactly the same as what we've just done down here. So the gradient, remember, is the rise divided by the run. Now the rise here is 50, we've gone up 50. The run is 1 hour. Okay, so doing the rise divided by the run is exactly the same as just using the formula triangle down here. Okay, number 2. Emma travelled to her grandmother's house and back. Down a bit. The distance time graph shows information about her journey. What time did Emma begin her journey? So this point here is between 7 and 8, so 7:30 a.m. Just going to give it a 24-hour clock, a bit easier. How far was Emma from home at 8 a.m.? So following this line up, she was 20 miles from home. How long did Emma stay at her grandmother's house? So we're assuming this is the point she reaches her grandmother's. She stays there and then she comes back. So she arrived there at 8:30 and stayed there until 10 a.m. So she was there 1 hour and a half. Or 1 hour 30 minutes, doesn't really matter how you give that answer. What time did Emma leave her grandmother's house? Well, we just worked that out, that was 10 o'clock. How far was Emma from home at 11:45? So this is 11:30, which means this must be 11:45. And she was, at this point here, halfway between 5 and 10, is 7.5 miles. And how far did Emma travel in total now? On the way there, to get to her grandmother's house, she's travelled 40 miles. She's now 40 miles from home. And on the way back, she must have covered another 40 miles. Okay, so altogether, she has covered 80 miles. Okay guys, thanks for watching. The next video will cover the next page.